let's get started. The first thing, I mean, for the final project, the TA, when TA tried to arrange like group matching, because some group didn't, find the matching group. I mean, but there are some. We have odd number of groups left. So at the end, the TA assigned, I think one of the big group contains 3 small groups. Okay, just want you guys to know that, because that was because like we have odd number of small groups. So that's since 2 groups form 1 large group, but at the end, 1 small group will be left out. So in order to avoid that, so the TA just randomly assign like 3 small group, one of the large group to contain 3 small groups. Okay, but if you happen to fall in that group, I mean that large group, I mean, don't be surprised on that. I mean the grading, everything will be exactly the same anyway. Okay, so that's for the final project, and today we are going to finish this RN chapter, and hopefully go on to talk about autoencoder. I mean, we including today's lecture. Okay, we have 3 lectures left. Okay, because like the 2 lectures in January, the first one will be used for the final exam. Okay, I hope by now you guys know we have final exam. Okay, the first week of the January. Okay, and the second week will be second week in January. It's actually the final week. The lecture that week will be used for the group presentation for the final project. Okay, and I will just like the previous semester. What I'm going to do is I'm going to order pizza. Okay, because our class starts at 1 o'clock, right? So I'm going to order pizza like around like 12 o'clock, and hopefully by 12:30, we should have pizza here, okay, and a drink, okay. So you guys are more than welcome to arrive earlier to enjoy the lunch before your final presentation, okay. So and that pizza is on me, okay. Just want you guys to know that, okay. So back to the lecture. Last time we talked about the layer normalization, right? We talked about like the regular normalization, batch normalization does not work well for the RNN. Okay, it's a little bit better than nothing, but really doesn't help a lot. On the other hand, layer normalization is an idea that was proposed by some other researchers, and it turns out to be more helpful to avoid RN. Make sure like the gradient like does not go like does not explode or like vanish during training. Okay, so but how do we implement the layer normalization? Okay, in Keras, okay, there's really no cell, okay, that provide layer normalization by default. Okay, so what we can do here is we could subclass the RN cell, okay, and then create the RNN cell with the layer normalization functionality in there, okay, so so this is the thing. Oh, okay, thank you. 谢谢。可以吗？ OK， 好好好，谢谢。So you can see this one we subclass the layer class, okay, to create the LN simple RNN cell. Okay, basically, okay, here I mean we have a state size, output size. Okay, because this is basically this one allows us to create a layer of layer normalized RNN cell. Okay, so you cannot just create a cell with layer normalization in it, because the layer normalization is done by layer. Okay, so you have to create it as a layer. Okay, so in there, okay, so you can see, okay, you could create multiple units, multiple RNN unit cells in this layer, and the activation function by default is set to be hypertangent. Okay, and I think there's really nothing to say too much about it here. Okay, the only thing that we can mention is that you can see we call Keras.layer normalization function prior to the activation function. Okay, so that's normally how we do it. Okay, we first compute the linear summation for each cell, but before we apply the activation function, okay, we try to do the layer normalization. So that's why you see this line is inserted between this simple RN cell and activation function. Okay, and this is like a basic structure. Okay, and in here is the core function is the kind of like a constructor for this this class. Okay, so you can see, okay, it takes two output. Okay, when you create this thing. Okay, and these two output. Okay, the output new states basically represent the same thing. Okay, because remember, for simple RNN, okay, the cell state and its output are the same. Remember, we talked about that, right? So if we have a number of simple RNN cell, okay, their outputs as well as their states will be kept here. So they will be they will have two different outputs. But these two outputs, even though I say that, I mean they actually are the same thing. Okay, are the same thing. And we also have a normalized output. Okay, we use here. I mean, be careful. We first call the self.layer norm. Okay, to calculate the layer normalized result, and then apply the activation function to get this norm output. Okay, and then you can see, okay, this norm output, okay, is returned twice. Okay, why do we return twice? Okay, it is for the same reason. Okay, because, well, for basic RN cell, the state and the output are the same, right? So we return two of the same things. Okay, so that's pretty much about it for this layer normalization version of the simple RN cell. sorry. So, sorry, okay. So I think I already explained like the code, okay, here. So I will skip this this slide. And so how do we use this class that we just created? Okay, it's very simple. Okay, just okay. Instead of using you know basic RNN, okay, for char.layers.basic.rnn. We use char.layers.rnn. This is like a generic RNN layer, okay? And inside here, okay, we try to provide we specify we want to create layer normalization version of the simple RNN cell. We want 20 units of that, okay? And the other part remains the same. I think we already explained, okay, the first two lines, why do we need to have return sequence to be set to be true, right? Because we want the output to remain to be sequential, okay? So we set the return sequence to be true, okay? So that it will output sequences like for each input, okay? It will not just output the last output only, okay? And the input shape, I mean, it's a none because the first line actually expect any number of input, okay? And that's about it, okay? And the last line, okay, we use time distributed to wrap the dense layer, okay, to allow the dense layer to accept the sequence input, okay? This part remains the same, okay? So we could use this one, okay, to predict the sequences, okay, that we discussed earlier. Where here, these sequences. Remember we talked about this. So this is the code that we can be used to do the same thing, okay? And also, okay, you could, okay, for the dropout, okay, we could also create a custom cell to apply dropout, okay? But, okay, for dropout, since the cell already has this functionality built in, so we really don't need to write our custom cell for that. Okay, you just need to specify the hyperparameter, dropout hyperparameter, which is like the dropout rate. Okay, and but be careful that there are two different dropout that we are talking about for the RNN cell. Okay, the first one is just a dropout. The second one is what we call recurrent dropout. You could, which can be set for basically for basic RNN cell or like for the future more complicated RNN cell such as LSTM or GRU. Which we are going to talk about today. Okay, so the first one, okay, the dropout, okay, basically define the dropout rate to apply to the input. Okay, so that once a while, okay, when if you throw a dice and it turns out that this node shouldn't participate in the computation this round, okay, the input will be disabled, okay, and the later, which is recurrent dropout, okay, it defines the dropout rate for the hidden state. So it is going to tell the cell, okay, not to use the hidden state for this particular step. Okay, so because remember the RN cell has two different input. The first one is just regular input. The second one is the feedback. Okay, if you really want all the input to be turned off, okay, from time to time, of course. I mean, then you need to set not only the dropout but also the recurrent dropout. These two things are actually, handled separately in the RNN, recurrent neural networks. Okay, so we already have such a hyperparameter to deal that you can set it up. So there's no need to create a custom cell to apply dropout at each time step in RNN. Okay, even though we could do that, but well, there's no need to do that. Okay, so with that, okay, we talk about dropout and the recurrent dropout. We talk about layer normalization. All these techniques, okay, can be used to alleviate the unstable gradient problem. Okay, and which allow us to train the RN more efficiently. Okay, so we sort of handle one of the two problems now, right? I mean, of course, like the unstable gradient problem. Okay, you have more than these solutions. I mean, last lecture we also talked about like gradient clipping. Okay, if you notice like a gradient become too large, you can also apply gradient clipping, and most of the techniques, okay, that you have learned in chapter 11, okay, which that is used to learn to train like deep neural nets, okay, should help as well. Okay, except of course the batch normalization and we don't. It doesn't. The ReLU, okay, doesn't help that much. Okay, but most of the other techniques, okay, that you have learned in the previous chapter should also apply. Okay. So we know how to deal with the unstable gradients. At least you have some tools at hand, okay, for that problem. So now, okay, we can focus on the second problem, okay, which is a shorter memory problem. Okay, shorter memory problem is like when you use RN to train a long sequence, okay, long sequence. The earlier sequence, the information in the earlier sequence, tend to fade away, gradually fade away. Okay, so here, I mean, textbooks use Dory the fish. I mean, you guys know Dory, right? Okay, you have seen the movie Finding Nemo, right? So Dory in that movie is the best example to talk about this problem. I mean, I should say she, right? I mean, it's a she. I mean, she really couldn't memorize like a long sentence. She probably can only memorize like short sentences. If you say something to Dory talk too much to Dory, I mean, she start forgetting about what you said earlier. Okay, so this is like the issue, the shorter memory issue. Okay, so to tackle this problem, okay, there are different types of cells which can memorize, okay, can have a long-term memory, okay, is able to memorize better, okay, have been introduced, okay. To be honest, like they are so successful, okay. Nowadays, okay, when we talk about RNN, nobody use basic RNN cell, Okay, nobody. The reason we use basic iron cell now, okay, I mean at least before this moment, it's just because like it's easier for you guys to understand. Okay, but from now on, okay, I would suggest you, okay, when if you need to create a RNN, okay, model, okay, don't use basic iron cell, okay. You should use, one of the two cells that we are going to talk about. Okay, the first one is called LSTM cell, okay, which is perhaps the most popular one. Okay, what is LSTM cell? Okay, LSTM, of course, it's an abbreviation. Okay, it stands for long short-term memory. Okay, long short-term memory. Why is it called long short-term memory? It's I don't know. It's really not a good name. Okay, but this name has been become like as I say, like this cell has become so popular. Okay, that everybody use it. I mean, to create RNN network. Okay, so this was proposed in 1997. Okay, and actually, there are a lot of changes, a lot of updates being made to this LSTM. So, so the current RNN cell structure is really very different from the one that was proposed in 1997. Okay, but the idea, of course, remains similar. Okay, so if you consider the LSTM cell as a black box, okay, you can just use it just like a basic RNN cell, except it performs much better. Training will converge faster. It will detect long-term dependencies in the data. So basically, it gives you all the desired property that you want. Okay, with just a switch of the cell type. Okay. It's very, very convenient, okay? And in Keras, you can simply use the LSTM layer instead of simple RNN layer, something like this, okay? So keras.layers.lstm, you can see, okay? You can use this command to directly create a layer of LSTM cell. Here we specify we want 20 LSTM cell. And the other part remains the same. Okay, so I will not go into detail for the other part of this but you get an idea. Okay, it's very convenient to use the keras.layers. Very convenient to use LSTM cell. Okay, and you could also use the general purpose keras.layers.RNN layer, and inside here, okay, you specify you want to use LSTM cell. So this approach will be similar to what we did for the layer normalization RNN cell. Will be similar to what we, here. You can see we use keras.layers.RNN, and then here we use LN simple RNN cell, right? So this second way to use LSTM cell is just like what we did for the layer normalization simple RNN cell. Okay. The other part again remains the same. Okay. So what's the difference between these two? Mostly they are mostly the same. Mostly the same. Okay, but I wouldn't say they are exactly the same. Why? Because, okay, if you use this approach, okay, when you do not have GPU support, okay, if your machine does not have GPU support, then, okay, these two ways to use LSTM cell will be exactly the same. Okay, but if your machine has GPU, okay, then it is recommended that you use this way to create a layer of LSTM cell. Why? Because, okay, this command actually has some optimization, okay, toward like a machine that has GPU support. Okay, so supposedly, like if your machine has a GPU, okay, then this method is preferred. Okay. Okay, just want you guys to know. Okay, so maybe, okay, it's better that you just remember this way. Okay, because well, when your machine does not have GPU, well, it just works the same way. Okay, it's just the optimization part in this implementation will not function. That's it. Okay, so. So how does a LSTM cell work? How can LSTM cell memorize better? Okay, let's have a look at the inside of the LSTM cell. Okay, let's open the black box. Okay, so this is the inside, the content of the inside the LSTM cell. Okay, so you have a C, you have an H. Okay, C and H are, you can say they represent the states of this LSTM cell. Okay, they represent the states of this LSTM cell. Okay, so what's the difference? Okay. C stands for the long-term state. H stands for the, you could say it's a short-term state. Okay, you could say that. Okay, and the H actually will be exactly the same as the output. You can see HT is the same as the YT. Okay, the same flow. Okay, is split into HT and the YT. Okay, so you could say the shortened state, okay, is exactly the same as the output. Okay, and here, okay, when this feedback comes in, okay, the CT-1, the HT-1 comes in. Okay, you can see we have actually 4 blocks here, right? Okay, this FC stands for fully connected network. Okay, fully connected network. So, in other words, okay, LSTM is a cell that contains multiple neural networks inside it. Okay. So let's take a closer look at this long-term memory. Okay, when C comes in, okay, first it goes through this forget gate. Okay, this forget gate it's a multiple, right? It's a multiplication, right? So it will be multiplied by the output of this FC. We call this forget gate. Okay, forget gate. Okay, and this forget gate is, of course, like controlled. Okay, just like the other gates, it is controlled by both the shortened state. Okay, the previous the feedback of the shortened state, and the current input. Okay, so it basically here. Okay, it control like because after all, okay. We are talking about, even though, okay, it's a long-term memory, okay, you cannot, because imagine that, okay, we have only like a fixed amount of storage, right? We have only a fixed amount of like space to store information, right? So you cannot expect, okay, we just keep adding the information to this C, okay, and expect it to just remember more and more content. It's not possible. It's not possible, okay? If you want the C, this long-term state to remember some new important information for a long run, you have to forget something first. You have to drop some information in order to put in some more information, okay? So that's the spirit, okay? Remember, like this is a fixed amount of space that, so you cannot put in like an infinite amount of information there. I mean, it's just not possible, okay? So first, it goes through this forget gate to forget some information that is no longer such important. No longer such important, okay? And then, okay, when it comes here, okay, first we use this this block. Okay, this is the only block you can see which is only fully connected network that use the hypertangent as the output. Okay, so it will try to extract from the previous edge, the shorter state, as well as the current input. It will try to extract the important information from these two sources. Okay, and this will be the something that is important. Okay, which and then when it goes here, okay, we use this. This is an input gate. Again, here, okay, we try to determine like try to determine what information should be kept long term, okay, by multiplying this output with this, because this is sigmoid, right? Remember, all these sigmoid will output a value between 0 and 1. Okay, so by multiplying this output with 0 to 1 value, okay, it's sort of like select certain information to be kept long term, okay, and then you will have that part of information to be put here, okay, to be added to the long term state, okay, and well, so this one will pass straight, okay, out as the next long term information, okay. And then, okay, this new CT, okay, the same thing, comes here, okay, comes here and goes through a hypertangent again, okay, to extract some information that is important as a short-term information. And this short-term information, again, it will be, it's going to be controlled by this gate, okay. So that like extract information from here to be the HT as well as the output. Okay. So keep in mind, okay, all these there will be a lot of like weights, biases in these fully connected layers, fully connected networks, obviously, right? So those weights and biases value will be determined, okay, when you train the network. Okay, so when you create a LSTM RN network, it is a network of a network. Okay, because each LSTM cell contains multiple networks. Okay. So by using this couple of network, okay, we are able to identify important information to be kept long term, and we are able to identify like a shorter information as well. Okay, so this is like the why LSTM cell perform better than the simple RN cell. Obviously, you can see there are a lot of like mechanism in building the LSTM cell that can perform, that allows the LSTM cell to perform much better than the simple RNN cell. Okay, but you may wonder, how come? You could understand. Okay, it will perform better, but you may wonder how come it trends faster, it converges faster, right? Because it is actually complicated, okay, to have all these things, including the network inside the LSTM cells, inside all the LSTM cells, to stabilize, okay, to converge, okay. But well, we have observed like something similar to that earlier, right? Remember, like for example, it's not necessary. A very simple activation function always converge faster. Remember, we talk about like a variation of LST of the ReLU. What's the name for that? Okay, it's like it's a linear function, okay, coupled with exponential function. I think it's called ELU, right? Remember, the ELU function is complicated, but when you use that to train the network, okay, it actually converges faster. Okay, so the content in the cell to be more complicated doesn't mean if you use that cell to create a network, it will converge slower. Not necessary. Okay, so this is a very good example of that. But of course, you could. I mean, you can still imagine. Okay, even though the training may be slightly improved, but you probably could have done it much better if you try to simplify the architecture of LSTM cell, right? Okay, so I will skip like the discussion, okay, because I already tell you guys like how it works, okay, and yeah, and so LSTM cell, okay, can learn to recognize the important input, okay, store it as in the long-term state, learn to preserve it for as long as it's needed, okay, and learn to extract the information whenever it is needed, okay. So this explains why the LSTM-based RNN have been amazingly successful. Okay, it can capture long-term patterns in time series, long text, and audio recording, and so on. Okay, so and this slide basically tell you like the mathematics formula, okay, behind that. I mean, so each W basically represent like what is computed in this fully connected layer, okay, in each of that. So but really like it shouldn't be too difficult to understand anyway. So I will skip these things. If you are interested, you can take a closer look. But basically, like each of them just like a very basic perceptron, okay, multi-layer perceptron calculations, okay. But just like what I said, okay, we could consider improving this LSTM cell, okay. Some people think, okay, the gate controller, okay, look at only the input and the previous shortened state, right, to determine, such as like what to forget, what to keep, okay, things like that, okay. But some people believe, okay, it would be a good idea to give them also the long-term information. Okay, so in other words, okay, at this moment, this is the current version of LSTM cell. Okay, you can see this gate, the input include the current input and the previous short-term state, right? But some people believe, okay, we should also provide like this long-term state, okay, as the input for this gate, which may allow the LSTM cell to perform better. Okay, so in other words, okay, we call such a thing as a peephole, okay, because we are sort of like looking in the future, okay. So they call this thing as a peephole. But you get the idea. So basically, in addition to this, okay, now this CT plus 1, CT minus 1 also, has also a link to go to this gate to control, like, what to forget, what to keep, things like that.